Right, this video is going to cover the entire alcohols topic from the Unit 2 part of the AQA chemistry. It's for that reason it may be a slightly longer video than some of the others. It's not going to go into particularly how to name alcohols in detail, that's covered in the nomenclature video, but it will go through how to make alcohols, particularly looking at making ethanol, looking at various sort of classes of alcohols, a bit about that and what classifies them as what, a bit of oxidation of alcohols, a bit of isomerism in there as well, and finally ending on a bit of dehydration of alcohols as well, and that should really tie in together the entirety of the whole topic really. So we're going to start though with not with too much really, as I said, not too much naming, with not really a lot of naming, but as I said, the easiest thing is to actually say, well, what is an alcohol? So an alcohol is something that contains, and I've got to be careful with this really, but something that contains this. Well, that's not right to say. It's something where this is the functional group. So the OH group is the functional group. So something like that. This guy here, this would be ethanol, and again, as I said, I'm not going to look at the naming of this, look at the nomenclature video for that, but this would be classed as ethanol. So we're talking about an OH group being present in this kind of molecule. Don't start worrying if you've got halogens and all other things. They're not going to test you on that kind of element. It's going to be fairly straightforward. So we're looking at this OH group as is shown here attached. It could be in the middle of the molecule, it could be on the end, doesn't matter. Okay, that will come into play later on, but right now, OH group being present. So the next thing then is to go into, and this is a part that I'm not particularly a fan of, it's making ethanol, and it's one of these kind of little bits of the topic where it's a bit environmental, looking at conditions and all the rest. It's not my favourite stuff, but it is, is required of you, so it's a fairly good idea to make sure you can do it. And actually it links in because this is ethanol right here. So this is our ethanol. Now there are two ways that we can make ethanol really. We've got one method which is fermentation, and the other method we've got is hydration of ethene, right there. So hydration of ethene and fermentation. As again, this is making ethanol, okay? Making ethanol. That's what both of these bits are going to look at. I'm going to go through this reasonably quickly, purely because it's one of these bits. The reason I don't really like it as much is that I don't see there being as much understanding really here. A lot of this is just learning and making sure you know the various equations on each side, and to me that's not my favourite part. There we go, doesn't matter. So fermentation, first of all, fermentation is turning sugar into alcohol. So sugar, glucose specifically, being this guy here, C6H12O6, we're turning it into alcohol. So CH3, and particularly ethanol here, CH3, CH2OH, and some carbon dioxide. Now we balance this up as such. And there we have it, nice and balanced. The confusion here, make sure obviously you look at the two carbons here, so that balances up 2 there, 3, 4 when you have 2 of these, 5, 6 takes there, and obviously our hydrogens and all the rest are balanced as should be. So requirements for this to occur. Well, key requirement is we need yeast, and this is the kind of whole idea of brewing. If you were to go into, which isn't necessarily a good idea if you're too young, but if you go ahead and you want to make some sort of homebrew type stuff, homebrewed beer, wine, cider, those kind of things, you're really putting yeast into a container and you're leaving it with some sort of fruit juice, some sugary sort of solution there. And what will happen is the yeast will naturally break this down. You can see it's just breaking down the glucose into the alcohol and into the carbon dioxide. What's quite important though is that it's an oxygen-free environment. So really what this is yeast's anaerobic respiration. This ethanol to yeast is lactic acid to us. So it's this essentially a toxic product actually, and actually what's annoying probably for the yeast is that when they produce this in solution, it actually kills the yeast off. The alcohol once I think it hits about 15% concentration or something, and from that point onwards you have to distill to make things like vodka and spirits and all the rest. So oxygen-free environment. Because we're dealing with this living organism, this yeast, temperature then, kind of, if you do biology, or certainly you should have done it, I would guess, at GCSE, 30 to 40 degrees Celsius, that optimum sort of 37, 38 degrees. We're talking about enzymes, living things. They need regulated temperature and all the rest. Advantages and disadvantages. So I'll do a little tiny table here. Advantages and disadvantages. First of all, advantage. Well, sugar's renewable. Okay, and as I said, you've just got to learn this. Sugar's renewable. A disadvantage to this, it's a batch process. What I mean by that, if you don't know what the term batch process is, basically you make a batch, then you stop, you take it away, and then you start again, you make another batch, and you start again, you make another batch. It's not continuous. We don't produce and take off, produce and take off. We have to start and stop, start and stop. And primarily this is because the old idea really is that the ethanol kills the yeast, and so you can't just keep going, because you'll just sit there forevermore with the same concentration, and it'll eventually just go off, and no one will be happy. Another advantage here is relatively sort of cheap equipment. I mean, you could actually do this at home, as I said. It doesn't take a lot of money at all to do some sort of brew your own beer, brew your own wine. It's very easy to do. Well, I hear it's very easy. I've never actually done it. You go into various shops and you can buy the kits and all that. The disadvantage here, ethanol needs distilling. And really what I'm looking for there, the idea of distilling there is not to increase its concentration and to make spirits and all the rest, but actually because we have to make sure it's pure. Otherwise you've just got this sort of mixture with the ethanol within it. We need to actually take the ethanol off as pure ethanol. Over this side then, hydration of, change colour for this, hydration of ethene. So the equation we're dealing with here is ethene, C2H4, and what we're doing is we're adding water to it, or actually I think we're adding steam in fact. And we're going to produce again C3CH2OH, and you can actually see what happens here is we have a double bond between there. The water is being added across there, one hydrogen one side, the hydroxide or the OH on the other side, forming as the delight that is our ethanol in this case, which I believe was just an electrophilic addition reaction. So, what do we require for this? What conditions? Well, we need a catalyst. There are a couple of catalysts you can choose from. We got to use the term conc here. If you don't, you'll lose a mark. H3PO4, or phosphoric acid as it's known, or conc again must be there. Sulfuric. Use either in an exam, it doesn't matter, but you must have the term. That's a P, by the way. It's terribly drawn. H3PO4, H2SO4. So phosphoric acid, sulfuric acid. Must have the term conc there. You do not want to lose silly marks like that. A few more things to learn here. Temperature, 300 degrees Celsius, and a pressure, 70 atmospheres. And again, a couple of advantages and disadvantages. I hate these kind of tables. Advantages and disadvantages. Advantage, it's continuous, so it's the opposite to the delight that is fermentation. Disadvantage, ethene, non-renewable, and you can kind of get around that as we'll look at later, but realistically speaking, ethene is going to come from crude oil, cracking and all the rest, which isn't particularly good. And another advantage is it's a purer product, requires less refinement. So there we go, that's making ethanol. All you've got to do is learn these, particularly learn the equation. If you do not learn the equations, you are going to you're going to give away a few marks there, which is stupid, absolutely just ridiculous. Learn those, learn a few of these bits, boom, 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 you've answered yourself a 4 or 5 mark question without really very little effort. No understanding there at all. Okay, next bit. Again, carrying on with this delight that is this ethanol, and now looking at ethanol as a biofuel, so another fantastic thing here. So ethanol as a biofuel. There's one particular thing that it does come up actually quite a lot. And I suppose particularly in this age where we're looking at global warming and climate change and all the rest, it's ethanol as biofuel, but particularly tied to the term carbon neutral. So this term carbon neutral, and that's a key phrase. They love to use that. And you see, businesses and all the rest are always harping on about how they reduce their carbon footprint, carbon neutral and all the rest. It's this real buzzword at the minute, and it seems to make people think that they're doing great things by reducing their carbon footprint and then becoming carbon neutral, which is obviously, you know, a good thing, but it seems to be something that people love to say. So why is ethanol as a biofuel? Ethanol, particularly ethanol produced via fermentation, is the key thing here. This is ethanol from plant material, hence the term biofuel. So just put that there actually. Fuel from plants. There we go. Ethanol is a biofuel. So how can it be classed as carbon neutral? Well, the way to do it is to look at two aspects of this. And the first is, well, we're looking at plants. So what do all plants do? Well, all plants photosynthesize. So let's look at the equation for photosynthesis. Now this is, if I get it right, it's been a while since I've done this, CO2 and H2O, so carbon dioxide and water, producing us our glucose, C6H12O6, just learn that thing, and also O2, which is delicious. 6, 6, 6, easily balanced. Learn that balance, that's what I would do. I won't bother going around and trying to balance it, but although it's not difficult to do, just learn it. Okay, and then we're looking at, well, carbon neutral. So this is our thing here. So what do we do is, well, we ferment that into inert terms to make the ethanol. So we would ferment this, and might see the same equation as before. A little bit of a recap for you. I'm going to abbreviate my ethanol now to C2H5OH. Either's fine. Do not write as a molecular formula. Never write molecular formulae. They're a waste of time unless you're specifically asked to do it. Do not do it. Fermentation, and then obviously if we're using it as a fuel, we've got to combust it. So we'll take something like our C2H5OH. We will react it with oxygen. We'll of course produce carbon dioxide and water. Now, although in terms of enthalpy of combustion wise, you would always keep this as 1 mole, because I'm producing 2 here, what I want is how much carbon dioxide ultimately I produce from combusting both of these. So I'll stick a 2 there, and then I balance it up, and I come out with 6 here, I come out with a 4 here, and I come out with a 6 here. Now the reason I've split these, you can almost see there's a divide between this one and these two, is that this is a carbon dioxide taking in process. These two are carbon dioxide releasing processes. And what I can say then actually, so if I look at this, and hopefully this will make some sense, 6 CO2 in, and here in total we have 6 CO2 out. So 2 here and 4 here. Now the reason this is classed as carbon neutral then is because actually there is, and actually I'll carry that on here, no net release of CO2. Learn that. Learn no net release of CO2. That's really good. They love that in an exam. That'll get you all your marks. They also love saying, well, why might ethanol not be classed as a carbon neutral fuel? Why is a company wrong in saying that its fuel's carbon neutral? Blah, 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 blah. And the reason for that is that although on paper it is true, you know, photosynthesis occurs, we take 6 in, we give 6 out from fermentation of our planting material and our combustion and all the rest, that's fine. But what this does not take into account, it does not take into account transport produces CO2. So this does not take into account transport. It does not take into account any machinery used to harvest crops, for example. So although you could get around, and some people I'm sure would argue that, well, these could run on ethanol and all the rest, the problem is you've got to produce the ethanol from somewhere, and therefore it's not classed as carbon neutral, always sort of behind. And that's the thing. So in terms of an exam, why is it not necessarily carbon neutral? This is your reason. If they're asking you why is carbon neutral, this is your reason. So you've got to balance the two up sometimes. It's a bit of argument type thing. Realistically, that's kind of all you really need to worry about in terms of the alcohols fermenting, so producing ethanol, and then leading on to ethanol being used as a biofuel and all the rest. Blah 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 blah, and then going through here to obviously being carbon neutral and why might it not be carbon neutral, etc. Now we get into a bit more of the stuff that I like, which is this is organic stuff, proper if you like. And I'm going to start here with it's going to be the structure of alcohols really, and the thing, and this is something that people do sometimes find quite confusing, and they shouldn't do. And it's very similar, if you've looked at other videos, to any kind of classification element, and alcohols fall into that same way of being classified. So alcohols can be primary, and I like using these numbers because it helps you a lot. They can be secondary, and if you've done biology, this will be certainly proteins and things, you'll come across this stuff. So primary, secondary and tertiary. I'm going to draw an example for each, and then just explain a little bit of sort of what's actually happening with regard to this, and what makes it primary, what makes it secondary, and what makes it tertiary. So the first one I'm going to draw here for primary is going to be ethanol. Now ethanol, as we know, CH3, CH2, OH. So I've done a nice full displayed formula there. Now, when you're looking at the class of an alcohol, and this is something you've got to be able to do in an exam, you absolutely need to be able to do it. You're looking, the class is denoted in the case of alcohols by what is attached to this carbon here, and it's the carbon that's attached to the OH group. So this carbon here. So look for that carbon. In this case, I have two hydrogens and I have a CH3 here. So I have a methyl group, so an alkyl group attached. One alkyl group equals primary. It's as simple as that. Okay, it is literally as simple as that. This one here, we'll go for secondary. We'll go for propan 2 on. Again, if you're struggling with this naming, you've got to get it sorted. Okay, get back, look at the video. If you know it already, brilliant. If you don't, sort it out, and just basically you've just got to be able to name stuff. Otherwise, it's going to come back and bite you in the bum. So CH3, CHOH, CH3, and in this case, this carbon, again, the one that's attached to the OH is what I'm concentrating on. It has one alkyl group, two alkyl groups, and therefore it is secondary. So notice these numbers: 1, 2, 2, and hopefully we can guess already 3. We're going to have 3 alkyl groups, and all I can do is change this one here, and I will draw it out in full. So CH3 as before, C with a, I'm going to just abbreviate that because I've run out of room slightly, and then a CH3 over here. So this guy here is now named differently. It obviously isn't what we had before. It's this time 2-methyl propan 2-ol. And look at this, follow the same rules. This is the carbon we're looking at. 1, 2, 3 alkyl groups. Look at that. 1 alkyl group, 2 alkyl groups, and 3 alkyl groups. That tells you the class, and it's as simple as that. 1, 2, 3. Look for the molecule. Look how many groups are bound to it. Circle them in an exam. Use a pencil in case you get it wrong. But do whatever it takes for you to actually understand what's happening. But take some time and work out the class, because actually what that leads into is this next portion. If you get the class wrong, you're potentially going to lose marks in this next part. And that is as follows. Alcohols can be oxidized. And we can oxidize alcohols in different ways. I'll go back here actually. We can oxidize them in different ways. Or rather, different classes of alcohols will oxidize in different ways. And to just go out there and do it. So sticking with this primary, secondary and tertiary, this being primary, secondary and tertiary again. Just undo that, change my colour. So actually I'll do it up here. So can this be oxidized? Yes it can. Can this be oxidized? Yes it can. Can this be oxidized? No it can't. Key thing here, this cannot be oxidized. That is important. It cannot be oxidized. A tertiary alcohol will not be oxidized. Okay, primary will and secondary will. Now the key thing here, primary, it can be oxidized to an aldehyde, and I'll go through this in a bit more detail in a second, and then a carboxylic acid. This one can only be oxidized to a ketone. This is the point here where people just go, oh god, I can't do it, there's so much to learn. Just sort yourself out and get it learned basically. Aldehyde carboxylic acid for the primary alcohol, secondary only to a ketone, tertiary does not get oxidized at all. And that can come up in various questions. Now you might be thinking, well, how do I oxidize something? Well, that's a great question. You oxidize, in the case of the AS, just use this, okay? Oxidizing agent is going to be, okay, and always use this, please. And if you're going to write it, you write it exactly as this. Acidified, that is important, potassium dichromate. And for those of you who are interested here, potassium dichromate, K2Cr2O7. Okay, so acidified potassium dichromate is the oxidizing agent, and when it's oxidized, okay, it goes from orange, could have chosen a better orange there, not going to lie, to green. That is the colour it changes when oxidation takes place. So it starts orange, it goes green when oxidation has taken place. So for example, this, the primary alcohol, will be oxidized, therefore the acidified potassium dichromate will turn orange to green. This one will be oxidized, therefore it turns orange to green. This one will not be oxidized, therefore it remains orange. That's very, very important. I'll come on to that in a second about sort of what that's going to look like and all the rest. In fact, at this point what I'm going to do is I'm going to go right up here and I'm going to look at the oxidation products. So I will come on to all that. I know this might be a little bit sort of jumping around here and there, but I want to go a bit more detail about the oxidation product. So, primary alcohol. And what I'll do is I'll pick ethanol because it's a nice, easy one. Everyone loves ethanol. So, CH3, CH2, OH. Now, what I can do here is I can react this to form it into an aldehyde. Now, you might be thinking, oh God, have I got to write a reaction with this K2Cr2O7? Well, you can, yeah, but it becomes a lot more difficult. So actually what you can do is you can just say, well, I'll add to this an oxidizing agent. And that is completely fine in an exam, okay? That works perfectly. And what you end up with is you end up with an aldehyde. Again, if you don't know how to name aldehydes, you need to go away and you need to learn it. But it is as follows. There we go. With this case, the functional group being CHO. You must write it in that order, CHO. COH implies you've got C with an OH joined on. CHO is the way that aldehydes are written. And this one here, you can see we've got all the bonds are correct. This would be ethanal. Okay, ethanal is this guy here. And what we've done is, if you think about it here, the way to sort of try and get your head around this is that basically what we've done is we've removed this, and you can think we've removed this and placed an O in. That's really the best way to think of it. We've taken the OH and the H off, and we've put an O here, double bonded, which of course means we've produced water as well. Water is produced as a byproduct there. The way this actually works is that the oxidizing agent actually takes both these hydrogens away, as opposed to actually slipping it in itself. It actually takes both the hydrogens to produce the water. But that doesn't matter. You just need to learn that ethanol, or know that ethanol can be oxidized to the aldehyde. In this case, looking at the structure, you can see that we lose the two hydrogens, and that produces the ethanol. I did say that could be further oxidized, and it's absolutely true that it can. So the ethanal, this one over here again, CH3, CHO. Again, same things before, just put an oxidizing agent, and it goes and it becomes the carboxylic acid. So this time what I do is I just slip, and I'll keep it like this. I slip that oxygen in here. Okay, that goes in here, and I produce my carboxylic acid. So that's very important. Okay, so what I've done is I've taken my ethanol, I've oxidized it to ethanal. That can then be oxidized to, and I'll just write this out, in this case, ethanoic acid. Okay, and that's quite a good one. Now, there's a couple of things on this really. If you want to oxidize and you want to only produce ethanol, and this is something you might have done, it's one of the PSAs, I often do it because it's quite a nice one to do. You basically react your ethanol with your potassium dichromate, your acidified potassium dichromate, and it changes colour and you produce the ethanal. And what you do is you distill it off. So if we want to produce ethanal, we distill. And the reason we do that, and we can do that, obviously we need to heat this, so we heat, and distill. The reason we do that is because we don't want this to be oxidized any further. And if we've got a load of potassium dichromate here, acidified potassium dichromate in our initial ethanol, then there's nothing to say that with a bit of heat this couldn't actually go right the way through to become ethanoic acid. But if we just want the aldehyde, we need to distill it off before it has a chance to become the ethanoic acid. And ethanol actually smells delicious. It smells a bit Christmassy. It's got a real sort of it's if you smell it, you know what I mean. It's almost cinnamony, appley. It's a really, really lovely smell. But the distillation takes this off. So this colourless liquid just comes off. If we wanted to make sure we'd got the carboxylic acid, we can do something different. Okay, and this is something that you've probably not actually used this before, but it's a process called, it's heating again, but would say you heat under reflux. And I'll put a picture here actually what that means. So this is heating under reflux. So basically what you've got is, normally when you distill something, you'd have your flask like this, blah 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 blah, and you'd have your thermometer, whatever, and you'd have the pipe down here, and you distill into your little conical flask. That is awful. Oh my, how is that even possible? Anyway, this is our condenser tube here, okay, our Liebig condenser. Now what you do for reflux is you actually flip it over and you turn it round, this bit, and you flip it right round so it's actually horizontal, and that's the condenser here. Now see, water in, water out. And what this does is, it actually means, it's quite clever way of doing things, is that when we heat this, we heat the solution at the bottom with our acidified potassium dichromate still, it will be oxidized and it will become the ethanol. But as it becomes the ethanol, what happens is the ethanol with a reasonably low boiling point gets evaporated. But because we've got this condenser tube here, actually, it doesn't matter. It just condenses, comes back down, drips down into here, where it can be reoxidized. And you keep doing this, and basically by heating under reflux, you can make sure that you've driven your oxidation right from your initial primary alcohol, ethanol, right through to your carboxylic acid. So you've heated under reflux. You don't expect it, as far as I'm aware, I've not seen this before, you're not expected to be able to draw reflux apparatus. It's a good idea to have an idea what it looks like, and if you've done it before, brilliant. I wouldn't have thought many people do this. Some certainly might do, but I wouldn't have thought many do. But if you're heating under reflux, then you just need to know kind of that this is how you can go right through to this. So if you want to stop at the aldehyde, you do a bit of terrible drawn distillation. If you want to go right through, you can use this idea here, which is heating under reflux. Okay. Secondary alcohol. It's a very similar idea. If we start with the one I showed you last time, which was the propan 2-ol, exactly as before, we use it, so I'll name this. So what we do, we add our oxidizing agent, our nice generic oxidizing agent, and this time what we do is, this is where the attack is taking place. You can see it's all really dependent on where the alcohol group is joined, and in this case, same reactions before really. CH3, there it is, CH3. Now this time we lose the same hydrogens as before, and so we're going to produce water. What we do is that we've now got this what's called a carbonyl group, the carbon double bond to the oxygen. It's not on the end of the chain, it's actually in one. Okay, so we've lost that hydrogen. Make sure that hydrogen is missing. 4 bonds to each carbon. That is right. And this is a ketone, and this is actually called propanone. If you wanted to name where this is, you could say it's propan 2-one, but I would be careful with that because there's nowhere else this group could be. If it was on the end, it would be propanal. If it's in the middle, it's propanone. So you don't need to number where it is. Okay, so in this case, although it would be at the second carbon position, that's how you would name it. Again, look at the video I made, it will explain all that. You don't need to in this case, and the same is actually true of butanone. You do not need to number where it is, unless of course you've got other things bonded on, but that becomes more difficult. Now in this case, if we look at this thing here, I'm not going to bother redrawing it because it's here, we have no hydrogen joined on. Like with our aldehyde, we had that other hydrogen where we could slip in the oxygen there. That can't happen here because we have no hydrogen missed there. So because the hydrogen is missing, it means that we cannot oxidize this further. So we end up with the ketone just being the final oxidation product, really. And again, I'll just nip that down here and show you that once more. So primary alcohol, secondary and tertiary, bam, 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 1, 2, 3. Alkyl groups, 1, 2, 3. Oxidized, yes, aldehyde, then carboxylic acid. Ketone, nothing at all. So that's very important, and the colour change is very, very important too, which again, I stressed that was the acidified potassium dichromate. What you need to be aware of here, and I'm not going to spend a huge amount of time on this really, because it can go on forever, is if you were given a molecular formula for an alcohol and you were asked, or you were given, say you were given an alcohol and you were asked to draw an isomer that was a secondary alcohol, you would obviously have to rearrange that, and that would go into fitting that it got the correct number of alkyl groups and all the rest. So you've just got to make sure that you're aware of what the question's asking, using those same molecular formula in the case of those isomers and all the rest. One thing I would like to to look at now is, imagine you've got 3 test tubes. This drawing is not going well for me today. So you've got 3 test tubes. In one we have, we'll go ethanoic acid. In one we have ethanol. This hasn't worked as well as I'd hoped. And in the other we have propanone. We can't have ethanol, it doesn't exist. And if you draw it out, you'll see why. So we have ethanol in one and we have propanone in the other. So these are our potential products of oxidation. So these would have come from our primary, and this would be our secondary there. So aldehyde, carboxylic acid, and ketone. And they might say, what tests could you do to determine which organic product was in which test tube? And you could say, right, well, I'm going to do some tests on this. So first of all, you could say, well, I'm going to test to see which one's the acid, and you could add something like a carbonate, and that would allow you to tell which one's the acid. And that would write off one of these. The other option you've got is that you could look for which is the test, therefore for the ethanol and the propanone. There's a specific test or a couple of tests that will have that both have the same expected result, or they work in a similar way. The result is different, but you get a positive test for the aldehyde, not for the ketone, is what I mean. And that test, the first one I think is the best one, is Tollens reagent. Now, Tollens reagent is essentially ammoniacal silver nitrate solution, which is actually it exists as this complex ion. So anyone who's doing A2, you would come across this. So this is essentially what we're doing here. It's got this nice little complex ion, AgNH3 or 2. Ooh, nearly got that plus. Now what happens is, if we add Tollens reagent to ethanol, the aldehyde, and we add it to a ketone, we'll get different results. An aldehyde, and you may have done this, and if you haven't, then it's a crying shame, asked to do it. This will give you a silver mirror. The ketone, no visible change. So NVC, no visible change. It will just remain as a colourless liquid. Okay. So silver mirror produced versus colourless liquid. And what I mean by silver mirror is something like this. So this picture here by Deborah Spurlock. Thanks, Debs. What you've got is, you can see here, boiling tube, and what actually has happened is, by having an aldehyde in here, by adding this Tollens reagent, which you would often make up, it's quite unstable, it could be quite explosive as well, you would make up fresh, which I believe is ammonia, silver nitrate, and sodium hydroxide. You add that to this, and this is what's formed, the silver. And what happens is, you reduce this complex down into actual pure metallic silver, which coats the inside of the boiling tube. And this here is that lovely silver mirror that you can see. With the ketone, you get no such wondrous imagery. You do not see this at all. So there would be no image. It would just be a colour solution, which makes for a much lesser photograph, really. Much less dramatic. The other way you could flip this round, and I actually realised as I was saying this that I'd actually started doing the wrong thing, is that you might be told that one contains a primary alcohol, one contains a secondary alcohol and one contains a tertiary alcohol. Now initially you could test, and that's so I'm on about one here's primary, one secondary, one's tertiary, but we don't know which. We need to decide which is which. It's the same situation as before, we need to decide which is which. So what you could do is you could add acidified potassium dichromate to all three. Now two of these two, would go orange to green. This one you would see no colour change at all. So this one straight away you could say, right, well I know which one's the tertiary. Boom, we've got rid of that one. So say this one was the tertiary. Done, absolutely fine. Now we'd still have two others that we need to think about. And in this case then you could actually distill off the ketone and the aldehyde, and you could then test them using the tolerance reagent. They love this kind of thing in questions, and specifically they love asking something like, oh, I'm running out of room rapidly. Oh, more room to decide. So they love saying in an isomer sort of type of question, give a test and result to distinguish between the following two compounds, and the compounds are A and B, and A looks something like this, and B, as you can perhaps guess, would look something different and would look like this. So the first thing is to say, oh well, I know that, and this all comes under the alcohols topic, I know that this is an aldehyde whereas this is a ketone, and therefore my test would of course be tolerance reagent. For A, the aldehyde, I would see a silver mirror formed, and for B, the ketone, I would see no visible change. There is one other test, and I should actually mention that I did say I was going to earlier on, but I forgot to, and that's Failing's solution, which if anyone's does biology or has done this test in the past, it's very similar to Benedict's. I think it contained, it's copper based, and again it's the idea we have some ions which are reduced, and in doing so they change colour. And really the positive test here is that we would get an orange precipitate, would be the aldehyde, ketone, nothing, no visible change. So another test there, Failing's solution. Right, final part. So the final thing I want to look at then is the idea of how we can dehydrate delightful alcohols, and we'll see a nice little space here, hopefully. Yeah. Right. So dehydration of alcohols. Now, this is one way that you can, well, essentially dehydrating an alcohol produces a ketone. It's the exact opposite of the hydration of ethene, and that very initial part. So quite simply, you could take something like ethanol, and you could dehydrate it, just think about what I'm doing here, to become, in this case, ethene and water. So we dehydrate to produce ethene and also to produce water. Now in the case of this, what happens is as follows. We specifically lose particular parts. Now, look at some conditions in a second. But when we carry out this dehydration reaction, this hydrolysis, essentially, I believe we would class this as. So we've got a, no, we wouldn't. So when we carry out this dehydration reaction, we lose this OH group and we lose this hydrogen. I always need to get that one wrong. So you lose the OH off one carbon, you lose the hydrogen off an adjacent carbon, and so you can get a variety of things can produce as we can reduce a variety of alcohols down. So if we give you another one, something like this, blah 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 blah. So in this case, we would lose this OH and we'd lose the H, and what we would produce is. So that remains the hydrogen there. We have a hydrogen here, still have a hydrogen there. We have a hydrogen there, hydrogen there, hydrogen there, which I believe is all balanced up nicely. Yep. And again, plus water. However, if we take something like this, I'm trying to think of an example now. In this case here, when we try and remove the OH from that carbon, when we look at our adjacent carbon, there is no hydrogen attached to the adjacent carbon. Therefore, we cannot dehydrate. So we cannot take this down to the alcohol, sorry, to the alkene. It cannot be done. So just be aware of that. I don't think they'd be mean in an exam and look at that type of thing, but certainly you do need to know that dehydration can occur. Now, I actually don't think conditions are required for this, but you can use, essentially it's similar to before. We can use an acid catalyst. So you could use something like conc H2SO for to carry this dehydration. I keep using the term dehydration, and I often should be a bit better really. And it's actually, this is classed as an elimination. So actually what you're doing is you are eliminating the water here. Just be aware that sometimes in exams they're a bit funny about things like dehydration. You know, what kind of reaction is this? You need to call it an elimination reaction versus a dehydration. Just be aware of that. But on that note there, I believe that is actually everything in alcohols. Again, if you think I've missed anything or you have any questions, please do stick that down in the comments. Yeah, there you go. That's the alcohols topic.